Today, we are diving into one of the absolute biggest shifts happening in AI. We're talking about the incredible leap from models that just, process words to systems that can actually see, hear, and truly reason about the world around them. This is the story of how AI is getting its senses.
So, for a while now, right, we've all gotten pretty used to AI as this super smart text machine. But what happens when that's just not enough? We're entering a whole new era where AI is starting to build a genuine, grounded understanding of our physical reality. The real challenge has always been, how do you bridge that gap between abstract words and the real world?
And this is the perfect way to think about it. A text-only AI knows the word gravity because it's seen it a billion times next to words like apple and Newton, but it has never, ever felt it. It's kind of like a scholar who has read every single book on the sun but has never actually felt its warmth on their skin. The knowledge is there, sure, but it's completely ungrounded.
So how do you solve a problem that fundamental? Well, developers are literally giving AI senses. This is the beginning of the multimodal revolution. And trust me, it's a genuine evolutionary leap.
Okay, so this gets a fancy name, Advanced Multimodal Reasoning, or AMR, and this is what it's all about. Giving an AI the power to seamlessly process and reason across text, images, video, and audio, all at the same time, kind of like we do. It's about building a complete, holistic picture of the world.
So we've covered the what and the why. Now for the really cool part. How does this actually work? How do you teach a machine to combine sight, sound, and text into a single, coherent thought?
Well, at the heart of it all is a huge architectural choice. When do you combine the senses? You could try early fusion, basically smashing all the raw data together right at the start, but that can get really messy. Or you could go with late fusion, where you only combine the final conclusions from each sense. The problem there is you risk missing all those subtle, crucial connections between them. As it turns out, the sweet spot is right in the middle.
And that sweet spot is called intermediate fusion. The best way to think about it is like a universal translator, but for concepts. It creates this abstract mathematical space where an image of a dog, the word dog, and the actual sound of a bark all get translated into a very similar format. This is the magic bridge that lets an AI understand the idea of a dog, no matter how it's presented.
Now, the piece of tech that makes this all possible is the transformer architecture. Its secret sauce is this incredible ability called cross-modal attention. So for example, if you tell it to find the fracture in this X-ray, it uses the concept of fracture from your words to scan the image, zeroing in on exactly the pixels you're looking for. It's a super targeted analysis, not just a blind guess.
And just look at how fast all of this is moving. We went from the foundational transformer back in 2018 to early bridge builders like Clip and Flamingo just a few years later. And now in 2024, systems like GPT-4o and Gemini can handle pretty much any kind of input you throw at them. We're talking any to any. The pace of this is it's breathtaking.
Okay, so that's the theory. But what does this mean for us, out in the real world? Well, the applications are already transforming industries in some absolutely incredible ways.
Let's start with healthcare. One of the big limitations of robotic surgery has always been the surgeon's lack of touch. But now, by fusing visual data from cameras with haptic feedback, systems like the Soroa robot can basically restore that sense. And the result? Surgeons using it reduce their grasping force by 46%. That's a huge drop in the risk of tissue damage.
And the ripple effect of that precision is massive. These AI-assisted robotic surgeries are already leading to a staggering 52% reduction in hospital readmission rates. So this isn't just some small technical improvement. It's a profound change in patient outcomes.
Now, this is going to sound like science fiction, but it is happening right now. By analyzing the chemical compounds in a person's breath, electronic nose devices paired with AI can detect non-small cell lung cancer with 94.4% sensitivity. It is a brand new, completely non-invasive way to screen for disease.
And it goes way beyond the hospital. In robotics, fusing sight and touch lets machines handle fragile objects without crushing them. Autonomous cars can now reason about complex road situations, not just follow a rigid set of rules. And in our cities, AI systems are watching traffic cameras to detect near misses with 87.5% accuracy, helping to prevent accidents before they even happen.
So, these models are getting incredibly capable. But here's the tricky part. How do we actually measure this new kind of intelligence? How do we know if these things can truly reason?
You see, the crucial point here is that reasoning has always been seen as a foundational distinguishing ability of human intelligence. It's what separates us. So if the goal is to build something that even approaches artificial general intelligence, AGI, it absolutely has to be able to solve complex reasoning problems. So to measure this, researchers developed what's called the MMMU benchmark. The best way to think of it is as a massive college-level final exam for AI. It has over 11,000 problems spanning 30 different subjects, from physics to art history, and they all require expert-level perception and reasoning.
And here's the scoreboard. As of late 2025, the very best AI models have just, and I mean just, reached the performance of the lowest performing human experts, right at 76.2%. Now that is an incredible milestone, no question, but there is still a significant gap to close before they get anywhere near the top tier of human expertise.
So that brings us to the final question. How do we close that gap? This leads us to probably the single biggest debate happening in AI right now about the path forward to achieving genuine, true intelligence. You've basically got two camps. On one side, you have the scale hypothesis. These folks believe that if we just keep building bigger and bigger models and throwing more data and more computing power at them, true understanding will eventually just emerge. But on the other side is the design hypothesis. This camp argues that brute force isn't enough. They believe we have to deliberately engineer intelligence with smarter, more efficient, maybe even brain-inspired architecture. How this debate gets resolved is going to define the entire next decade of AI. And it leaves us with this fascinating question to think about. Is the path to true intelligence paved with just endless data? Or are we going to need a better blueprint first? Right now, the answer is still being written.